Hello. So we saw in previous videos that with the impulse response, we could find the output of an LTI system for any other input. We could find whether the system was stable and whether the system was causal. In this activity, we are going to see how we can find the frequency response of the system by knowing the impulse response. And before we doing the proof, I just want to emphasize the result. So if you have a system, LTI, and the system is LTI, and you put a delta, Dirac delta at the input. So we put an impulse at the input. Again, common problem of students equating the Dirac delta as that was the impulse response. Not, that's the Dirac delta, that's the impulse function, that's the input. If your input equals to the delta, you put that into the system, you measure what the output is, the y of t, the output, which receives a particular name, h of t, that may be anything. Let's imagine the system is causal, so in this case, h of t is 0 for less than 0, in this case. You get something like that. As an example, h of t. It's a signal that characterizes everything. Like for instance, I just said the system was causal because h of t was 0 for t less than 0, etc. From this h of t, we can find the output, we can find causality, we can find the stability. We went over these things. Now we want to find the frequency response. Notice that when we computed the Fourier transform of the impulse function, what do we find? H of j omega, the Fourier transform, the frequency content of the impulse, this was a signal that had frequency content at all frequencies, and not only it has frequency content at all frequencies, but that the magnitude of the spectrum, it was equally distributed at all frequencies, at low frequencies, medium frequencies, high frequencies. So notice how wonderful it is. This is a signal that you send it and you are sending already all the frequencies. It's like if you were shifting all the frequencies like with a chirp. Even better than that. One signal, you send it throughout. So this is the ultimate test signal, right? And notice, by the way, that in discrete time, this is very well defined. It's a signal that is also the simplest signal. It's 0, 0, 0, 1, 0, 0, 0. It has all the frequencies represented. And so whatever the system does as a function of frequency, let's imagine in this case, we have something that perhaps behaves like this, like a low-pass filter for this impulse response. This is h of j omega. That's the frequency response, meaning how the system is going to respond as a function of frequency. Is this a low-pass filter, a high-pass filter, a band-pass filter, a band-stop filter? Right? Again, the fundamental idea is that you send a signal, the impulse, that had all the frequencies, so whatever now you do not have, if you originally were starting with all the frequencies, must have been cut by the system. Right? Signal with all the frequencies, see what the system does. Now, how do you find if you know the impulse response, if you know the output? Remember, the impulse response relates to the output when output of system when input is the delta. How do you compute it? Here you have it. The frequency response, h of j omega, is equal to the Fourier transform of the impulse response. And I have mentioned in the introduction of this series of videos that this was really cool. You put the impulse response in, and you get the frequency response, right? Why is this really cool? We have the continuous time Fourier transform as a tool for signal analysis. If you have a signal, I can find you the spectrum, the frequency content of the signal. And we did a lot of Fourier transforms in previous videos, right? The Fourier transform of the impulse, of a DC signal, of a shifted impulse, of a complex exponential sinusoid, of cosine, of sine, of any signal for which we have a Fourier series expansion, of decaying exponentials. When we did those Fourier transforms, not only we were looking at the frequency content of those signals, but if that happens to be the impulse response, meaning the output of the system when the input is an impulse, you also were doing system analysis. We are analyzing frequency responses. We'll say a little bit more about that later. So once again, you put the impulse response in, common mistake doing that for non-LTI system. If the system is LTI, and you get the frequency response out. How? Using your ideal spectrum analyzer, using the continuous time Fourier transform. So now you're using a technique for signal analysis to analyze systems. Why can you use it? Because there is a signal, the impulse response, in this case this signal, that completely characterizes the system. So that signal, you put it in the continuous time Fourier transform, which is our mathematical spectrum analyzer, and you're able to analyze the system. Okay, so that's great. That means that if we have this LTI system, if we put a sinusoid in, e to the j omega t, with any phase, so e to the some amplitude and a phase, j phase, this is our input. What is the output going to be? Remember that sinusoids are the eigenfunctions of LTI system, meaning they are the functions that are immune to the operation of the system, meaning if you put this in, you're going to get that out, a e to the j theta e to the j omega t out for a particular frequency. So you put a sinusoid for a particular frequency in, and you get a sinusoid of the same frequency out. Sinusoid in, sinusoid out, and not only sinusoid in, sinusoid out, you get a sinusoid of the same frequency out. You have the amplitude and the phase is still there, but how the system changed that sinusoid, like did it fall here, did it fall here, is all captured by the frequency response, multiplied times the frequency response. Notice that this, though, is a complex number, so it's going to affect both the amplitude, it's going to affect this part, as well as the phase. Is that clear? So we put a sinusoid in, we're going to get a sinusoid out. Is the sinusoid attenuated? For instance, was it operating at this, if you have a low pass filter, was it after the cutoff frequency and it gets attenuated? Well, all that, for the particular frequency for which you evaluate, omega 0, is going to be given by the frequency response, meaning you evaluate the frequency response at that frequency and you got it. Hopefully this is clear. Sinusoid in, sinusoid out of the same frequency if the system is LTI. How the system changes the sinusoid is all captured by the frequency response. And the frequency response is a function of all functions of omega, so you can just plug it in for the omega if this is a single sinusoid. More interestingly, If this is a sum of sinusoids, like if we were to do x of t equals sum of ak e to the j omega k t, k from minus infinity to infinity, if you put a sum of sinusoids in, the system is linear, so you can just pick each sinusoid out. Okay, so and these ones e to the j omega k, this is a set of sinusoids of different k frequencies. They may be harmonically related or not. This is one with line spectra. Ak is a complex number, so I'm already capturing the amplitude and the phase. So it's going to be there. Summing output is going to be a sum, k from minus infinity to infinity. Why is that? Linearity. And how are those amplitudes going to change? Well, it's going to be the frequency response evaluated at those frequencies. Right? So how cool it is that since we can denote, we are able to express any signal as a sum of sinusoids, which may be a discrete sum of sinusoids for signals for which you have a line spectra, or a continuous sum of sinusoids. And we know that sinusoids are eigenfunctions of LTI systems, meaning it's not like you have a square signal in and you may get a triangle out or a sinusoid out, right? So think of a square signal as if several frequency components. You pass it through a low-pass filter. You can, depending on how many harmonics you pick, you can go from a square to triangle to all the way down to just pick the fundamental harmonic and get a sinusoid out. In the case of sinusoids, it's different. You get a sinusoid in, you get the sinusoid out of the same frequency. Sinusoid here, sinusoid of the same frequency. But amplitude stays. How it changes is all evaluating the frequency response at those frequencies. So what have we found? By knowing the frequency response, you know everything of how the system is going to, these frequency selective filters, how it is going to react to all these other signals. Because in these signals, we're going to see what the spectrum of the signal is. Again, and going back, why is it that the frequency response could be found from the delta? Notice, the delta was a function that the spectrum had all the frequencies, and not only had all the frequencies, it's not like you had some of them less represented than the others, like something like that, or something like this. No, it had all the frequencies equally represented. So anything that is not there, think of an analogous filter mechanical, the system did it. Okay, so now that we understand the frequency response, being the Fourier transform of the impulse response, why the impulse response contains that information given that the delta function that we put at the input had all the frequencies, how once we know the frequency response, we are able to know what the system does to all the other signals, in part because the signals can be decomposed into sum of sinusoids, either discrete sums or continuous sums, and this is the equation. I can go ahead and just show you, prove you that that's the case. Now, in an exam, you will be expected to be able to, given an impulse response, like in the next problem, here you have an impulse response, what is the frequency response? Compute something like this. Or do this using MATLAB if it's a discrete time system or something like that. I'm doing something here that is more than what you will be expected in an exam, like are you able to derive that, right? So let's go over the derivation now. So to find the output in the time domain for an input, that is what we have to do here, if you recall, we could find it using convolution. Either x of t convolve with the impulse response, or h of t convolve with x of t. And that's what we're going to do. We have to find an output for a particular input, and we have to do it in the time domain. So I'm going to use the convolution integral. Notice this is the convolution operator. Y of t, therefore, is going to be the convolution integral. this convolution operator is equal to the integral from minus infinity to infinity. I'm going to use this form actually. H of tau x of t minus tau d tau. Again, this is convolution, which equals this integral that you have here, or here, that is equal to this. And it's how you find the output for any input, for any x of t, knowing the impulse response directly in the time domain. And it's more important that you understand the concept that this can be done in convolution than be computing convolution, toy convolution integrals of functions. We use the convolution, for instance, when we study FIR filters, to convolve a signal that was a noisy signal, like with a square signal, in order to clean it up, right? To implement filters. So let's apply this in this case to do this derivation. What is the input that we are giving? Well, this is the input, so let's plug it in. H of tau, a e to the j theta, e to the so all we have done, this is equal to our input, I have to do t minus tau, right? So t minus tau. Okay. We have h of tau, the impulse response, a e to the j theta, the phasor that contains the amplitude and the phase. We're going to partition this e to the j theta t e to the minus j theta tau v tau. Notice that we are integrating with respect to tau, so effectively what we have here is the integral from minus infinity to infinity of h of tau e to the minus j omega tau d tau, that's all grouped together, a e to the j theta is not a function of time, that's just a number, I can take it out, in or out, and e to the j omega t is also not a function of time. Notice that this is our x of t. When we put it into the system, if we put the eigenfunction, you get still the eigenfunction out intact, and everything that changes, the amplitude and the phase, is due to the frequency response. Notice that this is the h of j omega, meaning this is the Fourier transform of the impulse response. Notice this is the impulse response and this is the Fourier transform. So what have we found is that the output is given by a e to the j theta e to the j omega theta, just multiply times the impulse response. Now, you will evaluate that for a particular frequency. So if I give you a sinusoid of a given frequency, you get the sinusoid out of the same frequency, same amplitude and phase, but then you multiply it times something which you will evaluate at h of j omega 0 at that particular frequency, and it's going to give you a number with an amplitude. I'm going to call this h output e to the j theta output. So h will multiply times a, theta output will affect this theta. Is that clear? You put the sinusoid in, you get the sinusoid out. Where it is, and whether that amplitude is, let's imagine that this is a filter, low pass filter, and then goes down, this is omega, this is your h of j omega. This function here allows you, as a function of continuous function of omega, to see all those frequencies. whether your sinusoid was here, and so this is 1, we just went through, or it is here and it gets reduced, say, by 10, is something that you evaluate by evaluating h of j at the particular frequency. Or if you have a sum of sinusoids at all those frequencies. As I mentioned before, since you can express a signal as a sum of these sinusoids, you could do it by evaluating at each one of the frequencies, or if you were to submit all the frequencies, by looking at the frequency response, which, by the way, it is what you are doing when you're putting an impulse, because you're putting all the frequencies. Thank you.